In previous videos we have looked at light and how it behaves as a wave. In this presentation we'll look at light, how it acts as a particle when it's interacting with matter. In this video in particular we'll be introducing photons, and these are the learning outcomes required by SACE. As we've seen in previous videos, interference and diffraction are properties of waves, and when we look at light it exhibits some of these properties. So we can say light behaves as a wave. Now when light interacts with matter, however, we cannot describe it in terms of the wave motion, so there's other phenomenon that are occurring. Let's look at the double slit experiment, which describes light as a wave. So as the intensity increases, the intensity of the image produced, those bands, also increases. However, if we reconduct the same experiment in very low levels of light, so it's not in a pitch black room, but just a very dark room where only ambient light can go through the slits, we get something that's produced in image 11.3, and we can see there's these discrete dots that are produced on the image. If we repeat the experiment, we might get something like in 11.3b, and you can see these dots are in different places. If we leave the photosensitive film exposed for a short period of time, we get something like in 11.3a. If we extend that time and leave it exposed for an extended period, then we do end up getting the image in 11.2. So as the intensity increases, the images produce more of what we expect when light behaves as a wave. So looking at this, we can say that these dots are localized bundles of energy, which is the light, and over a period of time, the bundles of energy build up and we end up getting the image in 11.2. The dots that we saw in the previous image are the minimum unit of energy that light arrives. We can call this a quantum. So the minimum quantum of energy is actually called the photon. We can actually work out the magnitude of energy that each photon has by the equation E equals hf, where f is the frequency of the radiation or light, and h is a universal constant, being Planck's constant. Now this value is denoted on the screen, and you can see how small it is, being times 10 to the negative 34. So what this means is that every photon has an extremely small amount of energy. Now it only really matters when we put a lot of photons together, or photons are incident on an object, where the energy actually adds up and is of use. So we saw in the previous equation that energy is proportional to the frequency, and we know that the frequency is the speed of light divided by the wavelength, so that's that equation there. Speed of light is 3 times 10 to the 8, and if we substitute that into our equation, we get this equation at the bottom. So we've got two ways of finding out the energy depending on what values that we know of light. When we look at low levels of light and its interaction with matter, we see that light actually acts as a particle rather than a wave, and these particles are called photons. So one of the fundamental principles of particles is the conservation of momentum. Now momentum requires velocity and mass, but can we assign momentum to light, and does light have mass? Now you might recognize the equation on this slide, E equals mc squared, being Einstein's theory of relativity. Now we'll go into more detail on this later this year, but this implies that mass and energy are interconvertible, that is, matter can be destroyed and energy created. So although photons are constantly moving, they don't have a rest mass, but we can find a relativistic mass. So equating the equations, so we know our energy is found by h times f, but also our energy is equal to mc squared. So we can equate these, rearrange, and we find that the relativistic mass of a photon is given in this equation here, being h over lambda c. Now that we know the relativistic mass of a particle, or the photon, we can work out the momentum of the photon. So this is given by this equation here, P equals h on lambda, which is actually de Broglie's equation. Now the interesting thing about this equation is that we can see every particle has a wave characteristic, but it is only evident when the mass of the particle is extremely small, such as that of a photon. Looking at the previous equation and this diagram, we can see that as the energy of a photon increases, the momentum of the photon also increases. Now, we've seen from this presentation and the previous ones that light acts both as a wave and a particle. And we've been looking at light in the visible range, so in the middle of the spectrum here. Now, let's have a look at something that's higher energy. So with X-ray, for example. So we have an X-ray photon down the bottom here, high frequency. And we can see that this X-ray photon is a discrete, small particle, and it is of high energy and acts like a particle. Whereas if we look down the other end with our radio wave, it is longer because the wavelength's longer and acts more like a wave. So we can see that it's more difficult to demonstrate the properties of a particle of light when it's a radio wave than it is an X-ray photon.